When building a reception setup, commonly you will have an antenna somewhere and a receiver at some distance with a cable interconnecting everything. However, to improve reception, you might also consider adding in a low noise amplifier, preferably as close to the antenna as possible. This, however, begs the question: how do you provide power to the amplifier? Do you bring a new set of cables or use the already existing one? Hello and welcome back. Today I want to talk about a very simple circuit, on the surface at least. It's commonly used to combine an AC as well as a DC signal in multiple use cases, the main focus of today being RF applications. What I'm referring to, of course, is the bias T. So if you're curious, then keep watching. So first things first, let's look at the typical use case as well as the main characteristics of such a circuit. So as previously alluded to, if you have an amplifier at one end and the receiver at the other, with a signal cable in between, you still need to somehow provide power to the amplifier. While it's possible to drag an extra cable, this is not usually preferred since, well, it's an extra cable, and other than the extra price and inconvenience, it can also pick up quite a bit of noise. So the preferred solution is to use the existing cable and take advantage of the fact that you can carry signals of multiple frequencies through it at the same time, even some DC. And another thing to remember is that the various signals can go in opposing directions. The only important thing that needs to be done, therefore, is to separate the two. And this is where the bias T comes into play. In its most basic form, this requires two components. Z1 is something that has a very high impedance at DC, preferably infinite, but at the same time has a very low, preferably zero, impedance at the RF frequency. Usually, this is implemented as a capacitor. Then the second thing, Z2, is a component that has a very low, preferably zero, impedance in DC, but also a very high, preferably infinite, impedance at the RF frequency. And this is usually implemented as an inductor. So, using a couple of these circuits, we can combine the DC and RF signals at one end of the cable and then split them apart at the other end. Just to illustrate this operation, I created a basic circuit in which on the left side we have a DC voltage source and a 50 ohm RF load, and then on the right side we have a 10 ohm DC load and a RF signal, so a 10 MHz sine wave. So if we run the circuit, we can start to check out how the signals are passing through it. So first off, the RF bit, we have a 100 millivolt signal present on the signal source, and this is more or less identical to the signal present on the RF load. Then for the DC, we have a 10 volt source supplying a 10 ohm load, so we should have 1 ampere, and well, if we check the current running through our source, well, it's more or less that. So there's a bit of a drop because of the inductors, which have about 1 milliohm of series resistance, so this is to be expected. But the other thing that we can notice is that if we check the voltage present on the load, while it is almost exactly 10 volts, there is also a bit of an oscillation here. So it's very small, but there is something. So even though we're using relatively large value inductors, a very small part of the RF signal will still be leaking through. But anyway, from a distance at least, this circuit is working as expected. As long as the inductor has a high enough impedance and the capacitor a low enough impedance, both at the operating frequency, this is all that you will basically need. So, a bias T is a simple enough circuit, right? Well, in practice, you will commonly run into two major issues. First, as we've seen in the simulation, you will need to somehow keep the RF bit out of the DC path. This is especially critical to prevent oscillations or instability on the amplifier side. For this, the common solution is to simply add a capacitor or two. This way, any RF current that passes the inductor should have a local low impedance path to ground. Especially if the external circuit has a bit of built-in impedance and some more filtration, this should be more than enough to keep things under control. Now, what could possibly go wrong when you put a set of capacitors and inductors in series? Well, if we go back to the simulator for a moment and turn to an AC type of simulation, so I first built the initial circuit as a reference, so just to check what the wideband behavior of the circuit is, and well, if we run it and check the AC signal that reaches our load, we can see that at relatively low frequency, where the impedance of the reactive components is limited, we are getting some signal loss. But above about 1 MHz, all of the input signal is reaching the load. So we are getting the -6 decibels characteristic for a 50 ohm matched system. Now, if we were to modify the circuit a bit, so first of all, just remove the DC bit and add in a set of decoupling capacitors. So I just put in a set of 100 nanofarad capacitors and recheck the signal that reaches the load. Well, we are getting an extra dip when the newly formed LC circuit has a series resonance. Now, we could of course move this resonance if the component values were a bit different. So with this circuit, I'm using 10 nanofarads and 10 microhenries instead of the 100 nanofarad and 100 microhenry. And with this third circuit, the resonance has been moved a bit higher. However, this specific phenomenon could lead to problems if this resonance falls into the useful range of the bias D. Now, other than changing the component values, another approach would be to add in some series resistance. So just to change the Q factor of the series resonance circuit. So if we check this circuit and we'll compare it to the last one, well, the resonance almost completely disappeared. However, such a large value of series resistance would be problematic for the DC operation, since whatever current will be passing through this circuit will have quite a bit of voltage loss. So while this approach will work, its utility will be a bit limited. Now, the other main issue of this circuit has to do with the differences between the theoretical components and the practical ones. Capacitors have inductance, and inductors have capacitance. Now, if we start from one of the previous circuits as reference, so the one that had a 100 nanofarad decoupling capacitor and 100 microhenry inductor, we can compare this to see what happens when you're adding various parasitics. So let's just put up the reference signal, and first thing to look at is what happens when we add in the inductor parasitics. So here I added in a bit of parallel capacitance and a bit of series resistance. So if we check the response of this circuit, well, nothing really changed at low frequency. However, at high frequency, the parallel capacitance of the inductor will cause its impedance to decrease. So from this, we are getting an extra attenuation corner at high frequency. So we don't just have the low frequency one, now we have a second one. Then the next thing to consider is what happens when we also add in some parasitics to our capacitors, specifically the series inductance. So if we look at the response of this third circuit, well, we are getting some new resonances. Again, this will mostly show its head at high frequency, where it will cause various dips and resonances. Now, you can make various component choices to move these phenomena around a bit, but as long as you're using only reactive elements, this sort of issues will not really go away. The point is that while you can easily choose parts to achieve a relatively narrow bandwidth by choosing components that are used below their self-resonant frequency, getting the bias T to work over a wider frequency range requires a bit more work. Each individual component will have their limitations, but you can combine multiple ones to get a broader operation. This can be done for the capacitor, but more commonly it's reserved for the inductor. So there are two main measures in common use. First, in this small TV signal amplifier, we can observe that the inductor has a magnetic core, the black bit. While adding a magnetic core to an inductor helps increase inductance, another effect that appears at high frequency is that the core starts to absorb the magnetic field, in essence turning the inductor lossy. So while you get inductance at relatively low frequency, at high frequency you get a lot of resistance, thus reducing the Q factor and the possibility of any sort of resonances. Another measure that can be observed in this commercial bias T is the usage of multiple inductors of different values. So for the high frequency behavior, you use a small inductor and combine this with larger inductors for the low frequency behavior. And in this case, there's even a third, even larger inductor on the other side of the board. While all inductors have a magnetic core, you can further reduce the Q factor by adding some resistors in parallel. So to illustrate this principle, I just left a single bias T, and I will be looking at the RF signal that passes through it. So to keep things as realistic as possible, I'm using component parasitic values from a set of practical components from TDK. So the first circuit to look at is built with a couple 100 nanofarad capacitors and a 47 microhenry power inductor. So if we run the circuit and check the signal that passes through it, we can see that while this works just fine above 1 MHz, once you pass the 100 MHz marker, the loss starts to increase again. So with this particular set of components, you will be getting a flat behavior for about 2 decades. Now, in contrast, if you look at a circuit where the inductor was replaced with a ferrite bead, here the high frequency behavior looks much better, but the low frequency behavior was severely affected. So to try to get the best of both worlds, I put the two components in series and got this third circuit. So if we look at the output of this one, we can observe that we are getting a far better both low and high frequency behavior. So this red line is almost flat from 1 MHz up to above 1 GHz. Now, if I just remove these other traces and zoom in a bit, we can notice that we are getting some sort of resonance at around 40 MHz. This will be quite common when combining multiple components of different values. So the capacitance from one component and the inductance from another component can create various resonances. And that will lead to such dips. So one solution to this is to try to reduce the Q factor of the newly formed LC circuits, usually with parallel resistors or RC networks. So in this particular case, in the last circuit, I tried to add in a series RC circuit, so a 1 kilo ohm resistor and a 1 nanofarad capacitor. And this goes from in between the two inductors to ground. So if we check the response of this final circuit, well, we can see that even though the insertion loss is not ideal, at least our response is much more flat. So we removed our resonance. Now, in most common applications, especially in RF below a few gigahertz, building the bias T with inductors and capacitors is the most common way. However, under certain cases, especially the inductor can be quite problematic. So I found a couple more ways which might come in handy in certain cases. So first option to consider is replacing the inductor with a resistor. This sort of RC bias T is common in audio frequency applications like supplying a microphone. Since the supply current is so low, the large resistor is not really an issue. Now, you could of course use this at any frequency if the resistor losses are acceptable. However, the special thing to consider at low frequency is that an inductor would be so large it would be impractical. Like this, with the resistor, you also get a fixed impedance value over a wide frequency range. So there are some advantages to consider. At the other end of the spectrum, up into the gigahertz range, a common solution is to replace the inductor with a quarter wavelength transmission line. The idea is that at the frequency where this line is a quarter wavelength, the short circuit from one end, where the decoupling capacitor is placed, is seen as an open circuit from the other end, where the radio signal is. So while this is a narrowband technique, it will work well when inductors become impractical. And of course, the bandwidth could be increased by using a stepped impedance transformer. Last thing to look at today is how a bias T needs to be characterized. How do you check if the circuit is good or not? Well, there are three main things to look at: insertion loss, return loss or VSVR, and isolation. Now, while plotting these in the circuit simulator might seem straightforward, there are some things to keep in mind to get the correct values. So, to illustrate all of these, I took a basic circuit and used a .NET statement. So, for this first circuit, I terminated the DC and the DC plus RF ports with 50 ohm resistors and added in the signal source on the RF only port. So when we simulate the circuit, we can right click to add traces, and we can see that we have gotten all of the network parameters, including the S parameters, all of which are available in the plot window. So these are what we will be working with. Now, here's where things may get a bit confusing. So the main formulas that you will find in literature are as follows. You get the insertion loss, so how much of the signal is lost when it goes through the circuit, which is defined as -20 times the base 10 logarithm of the absolute value of the S21 parameter, and the return loss, how much of the signal gets reflected back into the source, which is more or less the same thing, but of the S11 parameter. Now, if we were to convert these one-to-one into LT-SPICE plot window syntax, we would be getting the following. So I put two formulas for each, just to be able to check the signal going in both directions. So from the RF port to the DC RF, and from the DC RF back into the RF. Anyway, the important thing to remember is that these formulas express the value in decibels. In other words, to get the correct values when plotting this, you will be needing a linear scale. So if you want to plot on the built-in decibel scale that LT-SPICE offers, you need to remove the bit that makes the linear to decibel conversion. And since in the plot window a linear value of 10 corresponds to 20 decibels, this will be the new formula that you get. So you just need 1 over the absolute value of the various S parameters. So if we plot a couple of these side by side, so I'm just copying these and pasting them, and just add another plot pane, add the other value. So the value we're getting in decibels from one of our graphs will be the same that we are getting on a linear trace from the other formula. So it's important to keep in mind which formula with which type of graph needs to be used to get the correct value. Finally, we have the VSVR expression. So you will be usually plotting this on a linear scale to begin with, so you shouldn't really have any issues. So just as an example, let's take one of these, add an extra plot pane into which we can put this expression. So now we get the VSVR and the insertion loss in this case. From a performance point of view, it's recommended to have a insertion loss below 1 decibel, and for the VSVR, usually it should be below 1.5, or if you're looking at return loss, it should be above 15 decibels. Now, while these values are easy to achieve in the simulator, the practical implementation will usually be a bit more tricky. Finally, to extract isolation, so how much of the RF signal gets into the DC path, you will need a couple more circuits, each with their own .NET statement. So you can apply only a single .NET statement to a single voltage source. So to get the various data, it's better to copy the circuit a few times and analyze each of them separately. So here, for the isolation, we have a similar story with the formula. The one that you commonly find in literature expresses the value in decibels, so you will need to modify it a bit. And well, we need to be careful with how we're plotting things. So I'll just take one of the formulas that can be expressed on the built-in decibel scale. Now, in general, practical values recommended for isolation are usually above 40 decibels. Final thing to mention is that while the circuit should be symmetrical, some differences will still appear. So it's important to check the signal going from each port to each other port. So you will be getting two values to check for isolation from each RF port into the DC port. And in a similar fashion, you will get two values to check for insertion loss and return loss. So signal going one way and signal going the other way. Usually the differences will be not that great, but small variations might still occur. In the end, while the biased circuit may seem trivial, once you start analyzing it in more detail, you will observe just how difficult it is to get a good performing circuit that operates over a wide frequency range. While it may seem easily doable in a circuit simulator, once you actually build it, some more issues may turn up. So next time I will attempt to build such a circuit and test it out a bit. But until then, Hope you enjoyed this video, and if so, there are more similar videos on my channel that you might want to check out. And if you want to be up to date with my latest releases, also consider subscribing. See you next time. Bye bye.